The second program for today is a DC-Cantilever for the analysis of cantilever walls. And here as well, if we start, we have some proposals for the type of wall. And this has the sense that we want to have a quite easy input if we don't need a very complicated wall. You see that we have many options. We have bending points in the wall. We have cantilever slabs. We can have a vertical spur under the footing, a sheet piling below, and so on. And if we really want to use this kind of complicated wall, you would have a very extensive input. We can change all these coordinates of the points, for example. We can have one or two cantilever slabs. So this input is quite complicated. If we don't need this type of wall, so with so many options, we can use a very easy type. So just a vertical wall with a horizontal footing, and we don't have so many parameters to enter, so this is much easier for the input. Now by default, we have two construction stages, one at the base of the footing, where the wall is constructed, and one with a certain filling, where we can activate passive earth pressure. To make calculation a little faster, I will delete this first stage. So we only calculate this type of construction stage. And here we have an input window for the basic parameters, and we have a graphical window for the output. And we can change the elements here, for example, moving a point. This is automatically adapted here in the input window. Or we can change the values here, and if I leave this field, it is automatically changed here in the graphics. So again, we have the basic functions at the left. And if I start with the basic parameters, we have again the selection of the analysis standard, where we can select Eurocode 7 for Germany or other countries. For the calculation of earth pressure, for example, in Germany, we have a local standard, so we don't use Eurocode 7 here. If you select Eurocode 7 for the earth pressure, this is used from Eurocode 7 Appendix 2, C2, which is based on the Danish norm. So for Germany, DIN 4085 is valid for the earth pressure. And for design of the wall, we have Eurocode 2 and other local standards. So here we select Eurocode 2 for Germany and have all the parameters predefined. There is one thing special for the cantilever walls. We have two types of earth pressures that we can use. One is especially for the wall dimensioning, which means we have the wall which is fixed here in the footing, and we have an earth pressure here on this wall. So this cantilever is fixed. This wall will not move very much. So normally we have an earth pressure at rest on the wall. And then for the stability analysis, where we have the total block of wall and ground, this might move much more. So here we can have active or increased active earth pressure for this total stability analysis. We can enter the depth of the groundwater. We can use compaction earth pressure like 25 kilonewtons per square meter to a depth of 2 meters. and the angle of friction at the base might be the angle phi of the soil, or it may be predefined differently. We may have a slope here in the ground. We can enter different loads, concentrated loads on the wall and distributed loads on the ground. So what you define here are load case combinations. That means that all the loads defined with the same load case name, for example, permanent plus variable, all loads with the same load case name are acting at the same time. So this is a kind of load case combination. And here we have a load value of 15, for example. This should be a live load. And so the safety factors are automatically adapted depending on the design situation, permanent, temporary, extraordinary. And then we have the construction phases. One is predefined here, and if we enter this with double click, here there might as well be a slope in the ground. The passive earth pressure normally is not activated fully, so we can have it reduced automatically, which means that the passive earth pressure is not more than the active load. So the passive earth pressure should not move the wall against the ground. And we can activate different types of verifications: sliding analysis, bearing capacity, settlement calculation, and slope stability analysis. So all these verifications should be calculated. And then we can switch into the results, full view, and have all the input parameters, soil data, and so on, safety factors and loads. Here have the earth pressure on the wall and the earth pressure for the stability analysis, the two different types as I described. And for a construction phase, we see the passive earth pressure, which is activated here. We have the loads from the wall itself and the earth blocks on the footing, and then the deformation and section forces of the wall. Then we have the ground pressure under the base. Verification against overturning is fulfilled for dead loads only and for total loads. The static equilibrium is fulfilled. Sliding safety is just exactly fulfilled with a utilization of 1. And the bearing capacity analysis under the footing is fulfilled as well. Then we have the calculation of the settlement on both sides of the footing and the slope stability analysis, which is fulfilled as well. And then we see this on in the graphics page. And here you see one important item, that at the end of the footing, we don't use a vertical substitutive wall, because as described in an older standard, this is not allowed in different cases. If we have a slope, if we have different soil layers, if we have block loads, we should not use the vertical substitutive wall, but the exact solution, which is here inclined under an angle of theta A apostrophe. So here you see the effect of the slope. So this is the substitutive wall where the earth pressure is acting on, and this is the block which might be moving and for which we calculate the bearing capacity below the ground, the sliding analysis, and the slip circle here for the slope stability. Finally, we see all the earth pressure loads on the wall, which is here we have the compaction earth pressure of 25, and then below the normal earth pressure. Here the special earth pressure for the stability analysis with the effect of the block loads on the ground. And we have the bending moment, shear force, and the deformation of this wall. After that, we have the design of the reinforced concrete, the maximum section forces. Here we have the maximum required reinforcement. And over the height of the wall, in sectional designs from top to bottom, you also see the minimum reinforcement, and in brackets would be the theoretical, statically required reinforcement, and the same for the foundation on the excavated side and on the supported side. Now we had just a verification of 1.0 for the sliding analysis. This was it was by luck. Normally we don't have exactly 1.0, and in this case we can also optimize the width of the footing at the left or at the right, and we can see which width of the footing we need to fulfill all the verifications. So for example, I'm going back to the input and tell the program to make an optimization of the left side. So we look at the left side of the footing here, what is needed for all these verifications. And if I go down to the construction phase, we don't need any width at the left side. Passive earth pressure is activated with 63%. And if we go down to the verifications, everything is fulfilled again. But we don't need here a cantilever at the left side. We just have one cantilever on the supported side with a width of 2.70 meters. And alternatively, we could as well optimize at the other side.